Okay, so we, in chapter 5, we are studying how to compute the area between a function and the x-axis from limits x equals a to x equals b. And in section 5.1, you were introduced to the notion that, well, one way to compute an area under a curve is to inscribe rectangles underneath the curve, and the heights of the rectangles are defined by either the left endpoint, the right endpoint, or the midpoint. And you can get an approximation of the area under the curve by taking a certain number of subintervals from x equals a to x equals b, computing the areas of the rectangles depending on whether you use left endpoints, right endpoints, or midpoints, and then the sum of the areas of those rectangles is going to be an approximation to the true area of the integral. And of course, if we take the number of subintervals and let n go to infinity, sometimes we can find the exact area underneath the curve. And we saw an example of that. And this really formalizes, this really leads to us into section 5.2, which is the definite integral. Okay, now the definition here, and I'm going to look up here. Okay, so this is the definition. Well, we saw in section 5.1 that a limit, hold on here, we saw in section 5.1 that a limit of this form arises when we compute an area. Okay, how many recall, you had a little time to work on 5.1. How many recall this kind of idea? It's been, I know it's been since before Thanksgiving, but how many do recall this? A little bit. I'm hoping maybe I'll get a few thumbs up. Okay, John says a little. Yeah, I mean, you're when Sebastian remembers it very good. I mean, when you take a value of a function, which is the height of the rectangle, and multiply it by the width of the rectangle, delta x, you get the area of a rectangle. And you're adding up all the areas of these rectangles, and as you let n goes to infinity, that means you're getting tighter and tighter rectangles. So let me just see here, one moment here. Maybe let me just see. Maybe it would help to go back a little bit here. Section 5.1. Yeah, remember this kind of idea? To find the area, to approximate the area underneath the curve, you pick a certain number of rectangles. Well, you define, like in figure 8 here, you have 10 rectangles, and the limits go from 0 to 1. So you would have 10 rectangles, each with width 1/10. And then the height of the rectangles, since you have r sub 10 here, you're letting the value of the function for every subinterval, the value, the right endpoint, you compute the value of the function at the right endpoint, and that determines the height of the rectangle. And as you see in figure 8, if you go to the second picture, they use more subintervals, n equals 30 subintervals, to approximate the area under this function. And then, and the function, I believe, was f of x equals x squared. And then for n equals 50, the third picture, you get even a better approximation. Okay, and this is, you know, if we're going to approximate the area underneath a curve, this is how you would go about it, right? This is how you would go about it. And it is, the function is y equals x squared. So what we're doing then is we're going to expand on this idea moving into section 5.2. Okay, did that refresh or help a little bit? Good, good. All right. Thank you, John. Thank you, Betsua. Thank you, Ian. All right. Thank you, Shako. Very good. Very good. So now then, now we move into section 5.2 here. And we're talking about the definite integral. So, oh, well, the definite integral, I mean, it's going to occur, this process where we have to find the area underneath the curve. And of course, that's the limit of the sum of the areas. Okay, the limits you're going to see are going to be involved in for finding lengths of curves, volumes of solids, centers of mass, force due to water pressure, and other work, the concept of work in physics. I mean, this is a very important concept. And what you're really computing here is what's called, you know, in this Formula 1 that they're showing you, what you're really computing is what's called a definite integral. Okay, so I'm highlighting all of this here. Okay, so the definite integral is going to be the sum of the areas of these rectangles that are used, that you choose. Okay, and you learned about the left endpoint approximation, right endpoint approximation. So like you had an example where sample points could be the left endpoints, sample points could be the right endpoints, you know, for defining the heights of the functions, the heights of the rectangles. And then you have the midpoint. Sample points could be midpoints. So the heights of the rectangles could be defined by the values of the function at the midpoints of each subinterval. But in fact, you can pick any point in each subinterval. You can choose your points any way you want, and you're going to be finding the area underneath the curve, and that's called a definite integral. That's called a definite integral. So a definite integral is if the function is positive from your limits x equals a to x equals b, then you are computing an area. Now, if the function is positive and then is negative, then you're not actually computing an area, but a difference of areas, and you're going to see that. Okay, but this is what we're trying to do now. What we're doing here when we're adding up these areas of the rectangles, and then taking letting, I want to say this right, we were adding up the areas of rectangles so we can approximate the area underneath the curve. But then if we take more and more rectangles, you know, we have more and more subintervals, we divide our area of interest, for, you know, from x equals a to x equals b, we divide it up into more and more subintervals. As we let those number of subintervals goes to infinity, then the sum of the areas of these rectangles is actually a definite integral, and that's what they're showing here in definition 2. Okay, that's a definite integral. And there's this symbol here, this kind of curly Q symbol, is what's called an integral sign. An integral sign. It's an elongated S and was chosen because the integral is the limit of a sum. Okay. In the integral, the function f of x is known, I'd like to kind of highlight it here, that function f of x is called the integrand. And A and B are called your limits of integration. Okay, A and B. I'd like to highlight that if I can, but it doesn't always let me. I do my best. You see it, A and B. They're called limits of integration. A is the lower limit. Okay, A is the lower limit, and B is the upper limit. And the symbol dx has no meaning by itself, but it tells you what integral you're integrating with respect to. So the dx just means you're integrating with respect to x. Okay, because you know your x-axis, that's where you're dividing up your subintervals. And this process is called integration that you're going to do. This whole process is called integration. And what we're going to do today is we're going to compute, we're going to do an example where we actually do integration, okay, where we compute a definite integral. Okay, are there any questions so far? So we're looking at these notes here that come after the definition. Second note is that this definite integral is a number. It does not depend on x. So what they have here, and I'm sorry, I'm trying to highlight it, is these three integrals. The first integral from a to b of f of x dx is the same integral from a to b of f of t dt. And that is the same value as the integral a to b of f of r dr. It doesn't depend on the variable. Okay, so that's just something to make you aware of. Okay. And we actually call in the definition here of a definite integral, this summation I equals 1 to n of f of xi star delta x, that's known as a Riemann sum. And it's named after the German mathematician Bernhard Riemann, who lived 1826 to 1866. You know, wow, only 40 years old. But, you know, back then, people didn't live so long sometimes. Okay, so, you know, we're really just sort of formalizing the idea now of adding up the areas of these rectangles. And we're really computing a definite integral when we do this. That's what we're doing. Now, they do have some other comments here. Well, first, are there any questions regarding the first three notes? Are there any questions at all regarding the first three notes that you see there? Okay, Sue is good, Kelvin's good, Rodrigo's good, wonderful, John's good. Okay, well, so of course, thank you. So of course what we're interested is evaluating these integrals. And in section 5.2, well, they have some figures here. They have some figures. It's probably worth looking at this. Figure 3, what they have here in figure 3 is they have a function f of x that is positive. First, it's positive. You know, it starts at x equals a and goes to x equals b. I mean, what I'm talking about is the rectangles. You're adding up the areas of the rectangles starting at x equals a and ending at x equals b. This is figure 3. And what you're doing here is you're finding an approximation to the net area. So you see, if the areas of the rectangles, the first three rectangles, are positive areas, because the heights of the rectangles in figure 3 are positive. The function's positive. But then, looking at the orange rectangles, those rectangles, every rectangle has a negative area, because the function values, which determine the heights of the rectangles, the function values are negative for the orange rectangles. And then the last three rectangles, the last three blue rectangles, the function now is positive again, And so the areas of those rectangles, 3 rectangles, are positive. So in that sense, when you compute the actual definite integral, which remember is the true area between the curve and the x-axis, you're going to get a net area. You're going to be adding a positive area and a negative area and a positive area. And this is what's one thing that's new in section 5.2. In section 5.1, when you computed areas underneath curves or approximated the areas, the curve was always positive. The function was always above the x-axis. But now we have to recognize that when we compute an integral could have a negative area as well as a positive area. It just depends on how the areas are situated throughout the curve, from x equals a to x equals b. Okay, so that's what figures 3 and 4 say. Are there any questions on that? All right. Okay. Now, for our purposes, we're going to always be dividing our subintervals up into equal width. Okay, but you don't always have to do that. And but we're not going to. You actually will see this in section 5.1. There's an exercise in your homework where the velocity data is not equally spaced. But we're not going to worry about that now. We're not going to worry about that now. Integration, you can get very, very technical when you talk about integration. And we just want to kind of keep it simple. We're going to deal with functions that are integrable, meaning you can find the integral, the area. You know, you can find those areas. We're not going to get too fancy. In graduate school, you can get fancy, right? But here we're going to keep things simple. So, all right. Like in example 1 here, they say write a limit of a Riemann sum as an integral. Write a limit of a Riemann sum as an integral. Okay, and what they have here is they want you to express the limit of this Riemann sum as an integral. Well, here's the solution. The limit of the Riemann sum is simply the integral, and the function you identify it based on the Riemann sum, based on the xi cubed plus xi times sine of xi times delta x. You recognize as x cubed plus x times the sine of x dx. Okay, so what they're doing in example 1 is they're just trying to get you used to to be comfortable with the fact that the limit of a Riemann sum of that summation is just equal to the integral itself. Okay, so some of the section 5.2 homework exercises are ones where you're just trying to get comfortable with the concepts. Now, of course, when we go to, and you know, they have some interesting footnotes here, you know, about Riemann and so forth, and you're welcome to look at that. Now, when we evaluate these integrals, we're going to be evaluating summations, and to evaluate the summations, we're going to need some formulas. So the integrals in section 5.2, these are the key formulas that you'll be using to help you. Hold on one moment. Sorry, I don't know, it just, yeah, there are 3 key summation formulas in 5, 6, and 7 that you'll be used to help you evaluate integrals. And you're going to be using these formulas for section 5.2. So I'll tell you what, let's go ahead. let's go ahead and look at an example right now. These formulas, by the way, they can be proven. They prove a few of them in the back of the textbook and one of the appendices, but you can take them on faith. You can take them on faith right now. So, okay, let's go ahead and get to an example here. The example I'm going to do with you is second example from the textbook. Okay, but I want to do it with you a little bit formally. Okay, so let me give you a moment to copy this example down. Okay, section 5.2. Okay, so we want to evaluate this definite integral here. We want to evaluate the definite integral. And in order to evaluate the definite integral, we first need to write down, well, we need to write this definite integral as a limit of an appropriate Riemann sum. Okay, that's how in section 5.2, we're going to evaluate this definite integral. Okay, because the definite integral, and we call it a definite integral, by the way, because in the definite integral, we have values. We have limits. We have actual limits. A bottom limit, which is a equals 0, and a top limit, which is b equals 3. So this is a definite integral. Let's go to the solution here. Let's start looking at the solution. So, like I had mentioned, we have to write the integral, and remember, of course, it's a definite integral. This little hand here. Hold on here. Okay, so to make that a little better. Okay, so we're evaluating the definite integral. Well, we're writing the definite integral as the limit of a Riemann sum. Riemann sum, just as a fancy way, I mean, technically it does have a meaning, but it's the summation. Okay, we're going to write the limit of our Riemann sum as n goes to infinity and evaluate the limit. And that's what I've done here. So the function, of course, is x cubed minus 6x. And in the Riemann sum, we have the sum here as I goes from 1 to n of well, the Riemann sum, what we're doing is we're adding up the areas of rectangles. Okay, every rectangle has a base that has width delta x and a height defined by f of xi, where xi is some point chosen inside each subinterval. And that point could be any point in the subinterval. It could be all left endpoints. It could be right endpoints in the intervals. It could be midpoints in the intervals. For ease of notation, for just because it's easiest, we're going to use right endpoints. So, how do we come up with these expressions here? How do we come up with this expression for f of xi and this expression here, 3 over n, for delta x? Well, I'll explain. If you're going to use right endpoints, then every subinterval, the x sub I in that subinterval, is going to be equal to 0 plus I times delta x. Okay, and the reason we have 0 here is because you're starting at x equals 0. That's your left endpoint. Okay, so like in the first subinterval, like x sub 1, is just going to equal 0 plus 1 times delta x. Okay. X sub 2, the point you pick in the second subinterval to determine the height of the rectangle, would equal 0 plus 2. I equals 2 there. 2 times delta x. And that gets you to delta x. Okay, so I want to be a little careful, how I kind of show it, but you have some function here. I'm just showing this in general. You have a function here, and let's say you have two subintervals, okay? Two subintervals. The function goes from x equals 0 to, in this case, x equals 3. And I'm not saying this function here that I've drawn is the same as this parabola. This is just kind of I'm trying to help you understand why these are right endpoints. So of course, your width of every subinterval is delta x. That's the width of every subinterval. Delta x. Trying to draw that the best I can. Okay, the width of every subinterval is delta x. So the right endpoint here for the first subinterval is just delta x. Oh, one moment, I'll get that. And then for the second subinterval, the right endpoint is going to be 2 delta x. 2 delta x. So that's what's going on here. That's what's going on. Okay, that's what's going on. And so in general, x sub I equals 0 plus I times delta x, which is 0 plus I times, okay, well, how's delta x defined? Delta x, and we learned this in the last class, you take the right endpoint, which is at b equals 3, subtract the left endpoint, which is a equals 0, and divide by the number of subintervals n. That's how you get your delta. And so x sub I is 3i over n. And that's why in our function, f of x equals x cubed minus 6x, well, you know, x sub I is 3i divided by n. So you have 3 times I divided by n cubed minus 6 times 3i over n. That's, you know, xi cubed minus 6 times xi. Okay, that's how you get f of xi. And then delta x is just 3 over n. So in order to evaluate this definite integral, we need to get, this the limit of this Riemann sum. And let me see, there's a question here. Ian says if your curve started at a equals 1, would x sub I equal 1 plus 1 delta x? Yes, it would. If your curve started at a equals 1, then your x sub I would equal 1 plus I times delta x. That's absolutely right. Absolutely right. Okay. So are there any questions? Are there any questions? Any other good questions so far? Okay. All right. Well, what I do here, I mean, basically now we're going to go to the next page and continue this. Okay. But I've made a little note. Hold on here. Get this off. I made a little note here that all I've done was, this is example 2 from your textbook. So I took figure 7 from the second example of your textbook, and in there they have the right endpoint approximation where you have 40 subintervals. And all they're doing, hey, if you have 40 subintervals, so in this figure 7 you have 40 subintervals, that means you have 40 rectangles, and they're adding up the areas of 40 rectangles. Every rectangle will have a width of 3/40ths, okay, and the height will be determined by the right endpoint of the height of the rectangle would be determined in each subinterval by the right endpoint of the subinterval. Well, the function evaluated at the right endpoint of the subinterval. And so they actually add up the 40 subintervals. You're never going to have to add up 40. You're not going to have to add up 40 rectangles. But the point is they get a negative answer. They get a negative 6.3998 for their right endpoint approximation. Now, that's not the definite integral. It's an approximation to the definite integral. But why is the area, well, why is R sub 4 negative? Why is the right endpoint approximation to the definite integral negative? And you notice in the graph here, in the figure 7, I have an A1 and an A2. A1, okay, John says the area below, which is A2, and that's negative area, that's bigger than the positive area above the x. So the area below the x-axis, which is A2, that negative area is more than the positive area, A1, above the x-axis. And so when you're computing the definite integral, you're computing in the net area. And so A2, or negative A2 plus A1 is going to be negative. Okay, so just wanted to kind of, sometimes students, when they get negative answers for their integrals, they are surprised by that, but you should not be surprised. That's going to happen a lot. Okay, so are there any questions before we move on to, and I'm not expecting you to copy this this figure down. It's in your book in example 2, section 5.2, figure 7. But are there any questions before we move on? Okay, well, let's go ahead and move on to finding the definite integral. So what I've done in the first step here is I've just rewritten what was on the previous page. And what I'm going to have to do is I'm going to have to rewrite this summation. I have to rewrite it. So for instance, the 3i over n cubed, well, that's going to be equal to 27i cubed over n cubed. Okay, I have to, start doing the math here. And then 6 times 3i over n is going to be the same as 18i over n. Okay, so I don't think, hopefully this is not a big deal so far, but let me know if you have any questions. Okay, well now let's talk about this step here. How do I go from the second step to the third step? Well, what I do is the 3 over n, which is the delta x, I'm going to distribute 3 over n to the two terms here inside the parentheses. And if I do that, that's going to get me then 81 over n to the fourth times I cubed minus 54 over n squared times I. Okay. Are there any questions so far? Okay, well then, now what I do is I have the sum here of the difference of two expressions. Well, that's going to be equal to the difference of the sums. Okay, I think that hopefully makes sense to you. I can write the sum of a difference as a difference of the sums. Are there any questions on that? Okay, well, now for the first sum here, the sum goes from I equals 1 to n, and the 81 over n to the fourth right here, this 81 over n to the fourth, in regards to the sum, we can treat 81 over n to the fourth as what? As what? Good, Sebastian, as a constant. So the constant is brought out in front of the summation. And similarly, for the second summation, the constant 54 over n squared is brought out in front of the summation. So what we have to do now is we have to compute the two sums. We have to compute the two sums. But in the textbook, they give you formulas to compute those sums. Their formulas 5, 6, and well, the summation formulas are 5, 6, and 7 in section 5.2. We're going to be using formula 7 and 7 and 5 in this case. So the sum of I equals 1 to n of I cubed is going to equal n times n plus 1 divided by 2, that quantity squared. And then the sum where I equals 1 to n of I, which is just, 1 plus 2 plus 3 plus 4 plus all the way up to plus n, right? That summation is going to equal n times n plus 1 over 2. Okay, so now my entire expression here, is a function of n only. Okay, and I can proceed to take the limit. Okay, and we can do that. So what I do is n over, just a little bit, n times n plus 1 over 2 squared, that's just the same as n squared times n plus 1 squared over 4. Okay. And what I do here for the second part is the 54 and the 2 reduces to 27 over 1. And then n times n plus 1 divided by n squared is just, that's just going to be n plus 1 over n, because the n here in the numerator simplifies with the n squared in the denominator, giving you just an n in the denominator. Well, 1 in the numerator and an n in the denominator. And so we end up getting here. We still have not taken the limit yet, but we want to do a little more simplification before we take the limit as n goes to infinity. But are there any questions so far? All right. May I move to the next page? Okay, Joe's good. I want to make sure I'm pacing myself well. Okay, Betsu is good. John's good. Rodrigo's good. Okay. Okay. Well, let's proceed. Actually, what I want to do, hold on here. Let me, Trevor says, shouldn't it be 27 over n for the bottom? It should be, Trevor. So for this second sum, or for this second expression, I do have a 27 in the top, and I chose to put the n then to move it over here. But yeah, it's 27 over n times n plus 1. But I just put the n over n plus 1. And incidentally here, n squared and n to the fourth, okay, that's going to reduce to 1 here, and then n to the fourth will reduce to, or simplify to, I guess what I'm saying is n squared over n to the fourth is 1 over n squared. Okay, so that being said, I can write the first expression as 81/4 times n plus 1 squared over n squared. Let me just, hold on. Yeah, that's right. That's absolutely right. First expression we can write as 81/4 times n plus 1 squared over n squared. But what I'll do is n plus 1 squared over n squared, and this is where you have to just, you know, we can write that as n plus 1 over n quantity squared. So I'm simplifying the sum so that I can take the limit. That's what we're doing. That's what I'm doing. And then n plus 1 over n, that quantity squared, is the same as 1 plus 1 over n quantity squared. And n plus 1 over n over here is the same as 1 over 1 plus 1 over n. And you see, once I get it, rewrite the expression in this form, it's easy to see that as n goes to infinity, in this expression, the 1 over n terms are going to approach what? As n goes to infinity, what does 1 over n approach? Well, hold on, and Ian, I will get there. I will get to your question. What I'm saying is the 1 over n approaches what? As, so you notice here we have 1 over n in two places, and we're going to let n go to infinity. So as n goes to infinity, what does 1 over n go to? What does that, what's the limit of 1 over n as n goes to infinity? 0, that's right. The numerator gets larger and larger and larger, so you're going to get like 1 over infinity in the limit. That equals 0. So hence, the 1 plus 1 over n is just going to approach 1. That's how you get 1. And when you take the limit, you get 1 squared, right, for the first part. And then the 1 over 1 plus n, that's just going to approach 1. And Ian's asking, how do we get the 81/4? The 81/4, well, if you look back in the previous, like in your notes, John. Well, Ian said we had. All right, so let me go. I'll come back to this, class. I'll come back to this. So on the previous page, you know, you have 81 in the numerator, 4 in the denominator, and then look at this n squared over n to the fourth. What does n squared divided by n to the fourth reduce to? 1 over n squared. 1 over n squared, that's right. And so that's how we get the n squared here in the denominator. And then I just, I have the 81/4 here. Ian, are you okay with that? Okay, good. So it turns out that our definite integral is going to equal -27/4 or -6.75. And that is if the integral may be interpreted as the difference of those areas A1 and A2. Okay, or you could think of that as A1 in the picture. Okay, in the picture, and I'll come back here. But let me just show you that picture here. So you have the A2 area, which is negative, and you have the A1 area, which is positive. So the integral is going to be the negative area A2 plus the positive area A1. Or you can think of that as A1 minus A2. It's the net area, And there's more negative area than positive area. So the net area, which is what the definite integral means, okay, is going to equal -6.75. Okay, so it's really a very nice problem because it teaches you a lot about it brings a lot of ideas together. Okay, one moment here. One moment, class. Let's see. Zoe says, can you solve this by splitting the integral and in the beginning and solving that way? Absolutely, you could, Zoe. You could, since the definite integral is the limit of a sum, any rules for sums would follow for integrals. So absolutely, we could split that up. And actually, I'm going to do another example with you, Zoe, in class where you see that. Okay, great. All right. Are there any other questions before we move on? Any other questions? One moment. All right. May I go to the next? Has everybody had a chance to copy this example down? Are there any questions before I move forward here? Okay. All right. Well, then let me go ahead and bring up the ebook again. Okay. Let me bring up the ebook. Okay, so here in so this is section 5.2. We were able to use we were able to compute the Riemann sum because we had those nice formulas that allowed us to compute the summations, and that's great. That's good. But sometimes those formulas, I mean, they're going to work for like polynomials. But if you have like an example 4 here, if you have something like this in A, where you want to evaluate the integral from 0 to 1, the definite integral from 0 to 1 of the square root of 1 minus x squared dx, you're not going to be able to use one of those summation formulas. So, but you can still evaluate the definite integral because the square root of 1 minus x squared is it's related to what? That function, the square root of 1 minus x squared is connected to what figure that you're used to seeing. Remember, this is y equals the square root of 1 minus x squared. I mean, let me just maybe what I'll do is go to the whiteboard for just a moment here. If you have y equals the square root of 1 minus x squared, which was in example 4, part A, sorry, let me just make that a little bit nicer. Okay, what intuitively do you want to do with that equation? If you want to relate it to some geometric figure, what intuitively would you want to do with that? Whenever you see a square root, what does your math intuition kind of tell you to do with the square root? Well, oh, okay, that's right. But I guess what I'm asking is, okay, square both sides. That's what I was looking for, Sebastian. I mean, we could square both sides of this. This is a function, right? This is a function, and a function's defined by xy coordinates. Well, right. I mean, give an x, you get a y. Given another x value, you get a y value. Well, if I square both sides of this equation, I'm going to get an equivalent equation. Y squared equals 1 minus x squared. And does that remind you of, and incidentally, I can write that as x squared plus y squared equals 1. What do we recognize that as? That's right. That's a circle. That's a circle. That's right, Sebastian. Oh, man, let me write that a little better here. Hold on here. I got to use the line feature. Hold on. What's the radius of the circle? Where's it centered? Okay, radius is 1, and the circle's centered where? What's the center of this circle? It's going to be the origin. That's right. That's right. So, okay, here's my beautiful circle. Beautiful circle. Okay, centered at the origin with radius 1. And our original function is y equals the square root of 1 minus x squared. Y equals the positive square root of 1 minus x squared. Is this function the entire circle? Is y equals plus the square root of 1 minus x squared, is that the entire circle? No, that's right, John. It's not the entire circle. It's going to be just half of the circle. But it's at the top half or the bottom half? Is y equals the plus square root of 1 minus x squared. I mean, we know this function's connected to a circle. It's going to be the upper half. That's right, because the y is positive. Okay, so this is this here then is going to be y equals square root, positive square root of 1 minus x squared. That's what it's going to be. Okay. All right. And of course, what we want to do now is we want to evaluate the integral. This is example 4. We'll get back to it. We want to evaluate the integral from 0 to 1 of 1 minus x squared dx. Could we, I mean, this is example 4. This is our definite integral. It represents some area, but again, we have to remember it's net area, really. I mean, in terms of my picture here, could I shade in the area that they're talking about? I mean, this definite integral here, could we, what, does anybody maybe think they could shade it in on the circle what the area is that this definite integral here represents? Do we have any volunteers? Tell you what, let me try something here. Let me try something. Don't write this down, but would it be, would this definite integral, the integral from 0 to 1 of the square root of 1 minus x squared dx, would it be all this top area here? Okay, Sebastian says no. Why are you saying no, Sebastian? We're taking the area of the circle from 0 to 1. That's good. So we're not going to have this area here. Okay, we're just going to have the area under in the first quadrant. So in other words, more simply speaking here, okay, the definite integral that you see here represents this area. Which is the area of 1/4 of the circle x squared plus y squared equals 1. It's 1/4 of the circle. Now, are there any questions on that? What would the area be of that quarter circle? Let's see, John says pi over 4, and you are right. That's right, because it's going to be, take the area of the entire circle, which is pi r squared. The radius is 1, so that's pi times 1 squared. But you're only finding the area of 1/4 of the circle, so that's pi times 1 squared over 4. That's pi over 4. Okay? So that's, for example 4, that's how you do the, that's how you get that definite integral, the answer. The answer is pi over 4. So they're using geometry. Okay, I mean, it's okay, that's fair. If you can use geometry to find your definite integral, that's okay. Okay, are there any questions? I want to return to example 4 and look at part B of example 4. Okay, one moment. I want to put the thing, what do you have? Oh, 20 feet. Okay, you know what I didn't do? I didn't put the towel under the door. Let me do that. Let me do that. Let me do that. Thank you, Kurt. You have to excuse me, class. I was just asking my brother to turn his TV down a little bit. All right. All right, now let me see here. Then let me go back to that problem. Okay, now we're looking at the second part. Okay, now this is the definite integral from 0 to 3 of x minus 1 dx. So what would be very helpful to do part B here? What do we really need to do in order to solve the problem? What's necessary? What helped us in part A with the function square root of 1 minus x squared? What was helpful there? It's worth 1,000 words. A picture. That's right, Ian. That's right, Trevor. A picture. So I'm going to draw the x minus 1. I'm going to draw that y equals x minus 1. Oh, y equals x minus 1. I know what that is. Okay, that's a line. So in figure 10, you draw y equals x minus 1 from 0 to 3. And I have a negative area A2 and a positive area A1. So the definite integral is just going to be the net area. That's A1 minus A2. Now they're saying A1 is equal to 1/2 times 2 times 2. Oh, how are they getting that? How are they getting that for A1? A1 here is, that area is 1/2 times 2 times 2. Well, what does A1 appear to be? A1 appears to be a area of a triangle. That's right, Kelvin. So 1/2 base times height. That's the area of A1. For A1, the base is 2, the height is 2. For A2, the second triangle, the base is 1 and the height is 1. And so you get negative 1.5, or you get positive 1.5. Okay, are there any questions on that? All right, if not, I'll move on. I'll move on. Okay. So in the book, they talk a little bit, they talk about using the midpoint rule to approximate the area under a curve. And you actually, or I want to be careful, they talk about using the midpoint rule to compute a definite integral. A definite integral is the net area under a curve. So you've seen the midpoint rule used before. We actually did it back last week in an example that we did. So example 5 talks about the midpoint rule. You know, you have a function like here from 1 to 2. You divide the function up into 5 subintervals. Okay, if you're going to use 5 subintervals, they say use 5 subintervals, and then you pick the midpoint of each. In figure 11, you pick the midpoint of each subinterval, and then evaluate the function at that midpoint, and that gets you the heights of the rectangle. So I think example 5, I think you can manage that just fine. I'm not going to worry about that because we've already talked about this kind of approach. But I want to move on a little bit here into, hold on here. Yeah, into some properties of the definite integral. Okay, so look at this first property here. Hold on, let me see if I can highlight it here. I think sometimes it just doesn't let me highlight. It's fine. The integral from b to a of f of x dx is equal to negative the integral from a to b of f of x dx. Okay, so here in the properties of the definite integral, they switch the limits. Instead of going from a to b, you go from b to a. But the effect is, when you switch the limits of the integral, it's gonna equal that integral. It's going to equal negative of the integral where the limits are switched back. And that has to do with this. Remember how delta x is defined. In the integrals are based on the Riemann sum. In the Riemann sum, the delta x is defined as b minus a divided by n. But if your integral goes from b to a, if the lower limit's b and the upper limit's a, then your delta x is going to be a minus b over n. But a minus b divided by n is the negative of b minus a over n. And so that's how the negative gets introduced in this formula here. Also, if you have an integral where a equals b, if your bottom and top limits are the same, then delta x would equal 0, because remember, delta x is equal to b minus a over n. So if b and a are equal, then delta x would just be 0 over n, which is 0, and hence, you get this result here. Are there any questions on that? And I think we'll be able to have some time to work a little bit on the section 5.2 exercises. I always like to have you work on material that we just learned. But let's just do a little bit more here before we move forward. All right, so there are other properties too of the definite integral. And remember, the properties of the definite integral are the same as the properties of summations. Okay, and here, let me see if I can highlight this. Here they have 4 properties of definite integrals. So property 1 says if you have the definite integral from a to b of c times c dx, in other words, your function is f of x equals that constant c, that's just going to be equal to c times b minus a. Now, why is that? Well, it's not hard to show, really. They have here in figure 13, they've drawn a function y equals a constant. Okay, that's a horizontal line. And the definite integral is the area underneath that function from x equals a to x equals b. Well, that's just the area of a rectangle. An area of a rectangle whose height is c and base is b minus a. So that's figure 13. That's used to prove the first result, to make you feel comfortable with it. The second result is the integral of sum of 2 functions is the sum of the integrals. Well, that makes sense because the sum of 2 expressions is just the sum of those separate sums. We saw that in the example that we did. The third property is that if your integrand is a constant times a function, you can pull the constant out in front of the integral. Well, that makes sense because that would hold for a summation too. And then the fourth property is if you have the integral of the difference of 2 functions, that's the difference of the integrals. So again, these properties follow from the properties of sums, of summations. Actually, let me show you something here. Let me show you something. Okay, so there are the properties of the integral. And if I go back, starting to appreciate this little arrow thing here. If I go back here, I'm sorry, I'm looking for, yeah, this is what I'm looking for. Notice here, you have 4 properties of sums. Okay, so But like Formula 9 says, if you have the sum where I goes from 1 to n of c times a sub I, you can factor the constant out in front of the sum. Formula 10 says if you have the sum of ai plus bi, that just equals the sum of those two summations. Formula 11 is similar. If you have the sum of a difference of ai minus bi, that just equals the sum of ai minus the sum of bi. Do these three properties of, I mean, really what I'm focusing on is properties 9, 10, and 11 for the summations. Do those properties make good sense to you? When you look at these properties for formulas 9, 10, and 11, okay, Betsu is comfortable with them, Ian's comfortable, Sebastian's comfortable. Okay, well, good, good. Well, when you see those properties, the properties for integrals, for definite integrals, are analogous to these properties for summations. They're absolutely analogous. Absolutely, and they should be, because definite integrals are defined as limits of summations. Okay, so if you're comfortable with those definitions, or those properties, I should say, they're not definitions, they're intuitive properties, then properties 2, 3, and 4 should hopefully be intuitive to you, because they correspond to those properties of the summations that we just looked at. How many find it helpful to see the properties of the summations, and then that makes you feel comfortable with the properties of the integrals? How many find that helpful? So what I'm asking is you were comfortable with the properties of the summations, those three properties, and do you see how formulas 2, 3, and 4, the properties for integrals, are analogous to the properties of the sums? Do you see it? Okay, Betsuo sees that. Great. Chaco, excellent. John, excellent. Wonderful, wonderful. Zoe's good with that. Sebastian's good. Excellent, excellent. That's what I was certainly hoping for. And so now we can look at example 6, and I'm going to just want to look at one more example here. Example 6 says use the properties of integrals to evaluate. Use the properties of integrals to evaluate this integral here. Okay. So, and this was a little bit towards what Zoe was asking, her comment earlier. If you have the integral from 0 to 1 of 4 plus 3x squared dx, you can take that integral and break it up into the sum of two integrals. But then the constants, the 4 and the 3 in each of the integrals, you can bring those out in front. Well, the 4, they're just going to leave the 4 in there for the first integral. But the 3, in the second integral, which is the integral from 0 to 1 of 3x squared dx, they're just going to bring the 3 out in front. And so now the integral from 0 to 1 of 4 dx, they use property 1. That's just going to be the area of the rectangle that has height 4 and base width 1. So that's 4 times 1 minus 0, that equals 4. And then in example 2, in section 5.1, they show, we actually showed this. No, we showed it for, I believe it was like integral of 3x squared dx, but the concept's the same. They actually show that the integral from 0 to 1 of x squared dx is 1/3. And so given that, then we're able to compute this definite integral using the properties of integrals. And the properties then show us that that definite integral is going to equal 4 plus 3 times a third, which equals 5. Okay, so, I mean, we're going to talk a little bit more about section 5.2 on Wednesday, and we'll also talk about section 5.3 on Wednesday. But you know, 5.2, if you're comfortable with the concepts in section 5.2, then section, well, you'll be that it'll be helpful. Let's put it that way. But are there any questions? Any questions on? Oh, did I lose you? Hold on. Did I lose? Hold on. Hold on. Did I lose the thing here? Hold on. 1 minute here, class. Let me bring that ebook. Hold on. Okay, so in the lecture, did this show on your screen? This example 6 that I was doing? It did show. Okay, all right. Very good, very good. Are there any questions on that? Okay, let me stop the lecture.